Chapter 7, X-ray interactions with matter. It is helpful for the radiographer to understand the way X-ray photons interact with matter for two reasons, and they're very important. First, it allows the radiographer to minimize the physical effects of X-ray photons on the patient that result in radiation dose and biological harm. Second, the understanding of the X-ray photon. Body tissue interaction allows the radiographer to better manipulate how the particular anatomic area of interest appears radiographically. Minimizing harm to the patient is extremely important, but also is producing a quality radiographic image. They're both integral parts of the responsibility of the radiographer. So this is where a LARA comes into play, as low as reasonably achievable. So we want to keep the dose low, but it has to be reasonable, right? So we want to make sure that we have enough dosage to be able to get that quality image that we're looking for, but also keeping the dose low to minimize harm to the patient. X-rays interact with matter in 5 different ways: classical interactions, Compton scattering, photoelectric effect, pair production, and photodisintegration. But the first 3 only occur within the range of energy used in diagnostic radiography, and we will talk about pair production and photodisintegration later. The first one is classical interactions, and it's also commonly known as coherent scattering or the Thomson scattering. In this scattering event, the incident X-ray photon will interact with the orbital electron of a tissue atom, and it changes its direction. In this interaction, the incident X-ray photon is of a rather low energy. It's going to be less than 10 keV. When such low energy incident photons interact with the tissue atoms, they are not likely to ionize, which means removing orbital electrons from their shell. Instead, the atom absorbs the energy of this X-ray photon, causing excitation of the atom, and then immediately releases the new energy in a new direction. Because the energy is re-emitted in a new direction, it's now a scatter photon. It is of equal energy to the incident photon, but it's going to travel in a new direction, hence the word scattering. It's going to scatter all over the place. Because of its low energy, most classical scatter photons are absorbed in the body through other interactions, and they do not contribute significantly to a poor image, but they do add slightly to patient dose. Compton interaction. So with Compton scattering, this occurs throughout the diagnostic range, but generally involves moderate energy X-ray photons. In this interaction, the incident X-ray photon enters the tissue atom. It interacts with an orbital electron, usually middle or outer shell electron, and then it's removed from its shell. In doing so, the incident photon loses up to 1/3 of its energy, and it's usually deflected in a new direction. So continuing with Compton interactions, this interaction does 3 things. First, it ionizes the atom, making it unstable. The ionization in the body is significant because the atom is changed and may bond differently to other atoms in the body, potentially causing biologic damage. If one of the middle orbital shells is involved, a characteristic cascade, which is where the outer shell electrons filling the inner shell vacancies, and they emit X-ray photons. This also results, creating characteristic photons just as in the tube target. But here they are called secondary photons. So these secondary photons are X-ray photons, but of a rather low energy variety. These photons generally contribute only to patient dose. Second thing it does is it provides the ejected electron. This is called a Compton electron or a secondary electron. This ejected electron leaves the atom with energy enough to go through interactions of its own in other atoms, which are next to it. So they're adjacent atoms. The type of interaction with the Compton electron depends on the energy it has and the type of atom that it interacts with. And then the third thing that it does in this Compton interaction is the incident photon is deflected in a new direction and is now a Compton scatter photon. So it too has enough energy to go through other interactions in the tissue or exit the patient and interact with the image receptor. So the issue with the Compton scatter interacting with the image receptor is that it is not following its original path through the body, and it strikes the image receptor in the wrong area. So by doing this, it contributes no useful information to the image, and it only results in image fog. Because most scattered photons are still directed towards the image receptor and result in image fog, it is desirable to minimize Compton scattering as much as possible. So Compton scattering is one of the most prevalent interactions between X-ray photons and the human body in general diagnostic imaging, and it's responsible for most of the scatter that fogs the image. The probability of Compton scattering does not depend on the atomic number of atoms involved. Compton scattering may occur in both soft tissue and bone. The probability of Compton scattering is related to the energy of the photon, and as X-ray photon energy increases, the probability of that photon penetrating a given tissue without interaction increases. So it's directly proportional. However, with this increase in photon energy, the likelihood of Compton interactions relative to photoelectric interactions also increases. Compton scatter photons may travel in any direction from their point of scattering. A deflection of 0 degrees means that no energy is transferred. So those photons scattered at 180 degrees represent maximum deflection and maximum energy transfer. But keep in mind that the scattered photon still retains about 2/3 of its energy, and this is one reason the radiographer should never stand near the patient during the exposure. Some Compton scatter photons exit the patient and would expose the radiographer. So not only are you getting the primary beam, but you're also getting these Compton scatter photons coming from the patient. So never ever hold a patient, don't stand in the primary beam. We always want to get somebody else that does not work directly in the radiography field to help hold a patient. So this is why shielding, lead aprons, lead gloves is necessary during fluoro exams and any other procedure in which you, the radiographer or another healthcare worker may be near the patient and X-ray tube during the exposure. It is important for the radiographer to remember that Compton scattering is the major source of occupational exposure. Photoelectric interactions occur throughout the diagnostic range 20 to 120 kVp and involve the inner shell orbital electrons of tissue atoms. For photoelectric events to occur, the incident X-ray photon energy must be equal to or greater than the orbital shell binding energy. In these events, the incident X-ray photon interacts with the inner shell electron of a tissue atom and then removes it from orbit. In the process, the incident X-ray photon expends all of its energy and is totally absorbed. You can see in figure 7.4, which is shown here, the total absorption of the incident photon and the characteristic cascade creating the secondary X-rays. So you have the incident photon and then the ejected photoelectron, and coming from that incident photon and where it hits that ejected photoelectron, you can see those secondary X-rays going out of the atom and out of the shell. The resulting ejected electron is called a photoelectron. The energy transfer between the incident photon and the inner shell electron is equal to the incident photon energy. minus the binding energy of the orbital electron. The energy transfer constitutes the energy of the photoelectron. In soft tissue atoms, the energy of the photoelectron is nearly equal to that of the incident X-ray photon because the binding energy of the soft tissue atom is very low and more is left over as kinetic energy for the photoelectron. In bone, the energy of the photoelectron is less because the orbital electron binding energy of bone atoms is greater and the incident X-ray photon has to expend more energy to remove it, leaving less as kinetic energy for the photoelectron. So it really does depend on how thick or how dense the soft tissue or skeletal, whatever the photon is going through, it really depends on the density of that area. In either case, the photoelectron has enough kinetic energy to undergo interactions of its own before filling a vacancy in another atom elsewhere. Note that this absorption that constitutes photoelectric interactions contributes significantly to patient dose accrued with each diagnostic image. Although some absorption is necessary to create an X-ray image, it is the radiographer's responsibility to select the technical factors that are going to strike a balance between image quality and patient dose. So with the image quality, that is the absorption and transmission of X-ray photons needed to produce a good image. And then we're also looking at the patient dose. So again, here we're talking about a LARA, as low as reasonably achievable. We also talk about risk versus benefit. So we do have the risk of the X-ray procedure, but we also have the benefit of the patient getting the X-ray image done so that they can be diagnosed and treated. In photoelectric interactions, as with Compton interactions, the tissue atom is ionized. In the case of photoelectric interactions, the inner shell vacancy makes the atom unstable. To regain stability, a characteristic cascade occurs, producing secondary X-ray photons. This cascade is the same phenomenon that occurs with Compton interactions that produce secondary photons. Again, these secondary photons are of low energy and are absorbed by the body in other photoelectric events. The absorption of these secondary photons also contribute to patient dose. The probability of photoelectric interaction depends on the energy of the incident photons and the atomic number of the tissue atoms with which they interact. For PE interactions to occur, the incident X-ray photon energy must be greater than or equal to the inner shell binding energy of the atoms involved. The tissue atoms. The greatest number of PE interactions occurs when the incident X-ray photon energy is equal to or slightly greater than the inner shell binding energy of the tissue atom. As the incident photon energy begins to exceed the inner shell binding energy of the tissue atom, the chances of photoelectric interaction begin to decline, and the chances increase that it will penetrate the tissue being examined. This function is a cubic relationship. That is, the probability of a PE event is inversely proportional to the third power of the X-ray energy. What this means to the radiographer is that if a KVP range is too high for the anatomic part of interest, less absorption takes place and some absorption is necessary for image formation. The probability of photoelectric events is directly proportional to the third power of the atomic number of the absorber. What this cubic relationship means to the radiographer is that when he or she makes small changes in the KVP, there are small changes in the atomic number of the tissue due to the anatomic variations or sometimes a pathologic condition. So large changes in the probability of PE events will result. With tissues, the higher the atomic number of the tissue atom, the greater the number of the photoelectric event. Such atoms are more complex, that is. So they have more electrons and stronger binding energies and are more likely to absorb the incident X-ray photon. This is why bone shows up as a lighter shade on the radiographic image. In bone, more photons are absorbed, which means fewer photons are exposing the image receptor, resulting in the lighter shades of the image. Pair production is one of the two with photodisintegration that are not involved in the image production. So pair production occurs only with a very high energy photon of 1.02 MeV or greater. The interaction occurs when the incident X-ray photon has enough energy to escape interaction with the orbital electron and interact with the nucleus of the tissue atom. In that interaction, the two particles are produced: a positron, which is a positively charged electron, and an electron. You can see here in figure 7.5, this is a pair production event, and the very high energy photon interacts with the nucleus, causing the release of a positron and an electron. All right, pair production again. So for these particles to exist, they must have energy of 0.51 MeV, the energy equivalent of an electron. If the photon has energy greater than 1.02 MeV, it is shared between the two as kinetic energy. Both particles travel out of the atom. The electron undergoes many interactions before coming to rest in another atom. The positron is an unnatural particle, and as such travels until it strikes an electron, causing an annihilation event. In this annihilation event, the positron and the electron interacts with are destroyed, and their energy is converted into two X-ray photons that radiate out of the atom. Pair production does not occur in radiography because the energy levels required exceed the range that we use in diagnostic X-ray production. The last type of interaction between X-rays and matter is called photodisintegration, and this again is the other one that is not used in creating a diagnostic image. Photons with extremely high energies of more than 10 MeV may strike the nucleus of the atom and make it unstable. In photodisintegration, the nucleus of the atom involved regains stability by ejecting a nuclear particle, such as a proton, neutron, or an alpha particle. Like pair production, photodisintegration does not occur in radiography because the energy levels required far exceed the kVp range that we use for diagnostic X-ray image production. So if you look at the figure shown here, 7.6, this is photodisintegration event. The very high energy photon interacts with the nucleus, causing the release of the nuclear particle to regain stability. Differential absorption is the difference between the X-ray photons that are absorbed photoelectrically versus those that penetrate the body. It is called differential because different body structures absorb X-ray photons to different extents. Anatomic structures such as bone are denser and absorb more X-ray photons than structures filled with air, such as the lungs. Shown in figure 7.7 here, we can see differential absorption. X-rays interact with the body in one of three ways. They penetrate to the receptor, which is your IR, your image receptor. They scatter in a new direction, or they are absorbed in the body. When radiographers speak broadly about differential absorption, how the X-ray beam interacts with tissues of the body, they may speak of transmission versus absorption. So transmission refers to the X-ray photons that pass through the body and reach the image receptor. It is desirable for some of the X-ray photons to pass through the body area of interest, or no image would result. So we have to have that. And then X-ray photons reaching the image receptor create the dark, less bright shades of the image. Absorption refers to the photons that are attenuated by the body and do not reach the image receptor. Absorption has the opposite effect on the image as penetration. So recall that these photons are absorbed photoelectrically and will not reach the image receptor. This lack of exposure to the image receptor results in the lighter, brighter shades of the image. It is also desirable to have some absorption, otherwise the image would be dark. It would be completely dark and have no shades of gray. Again, absorption depends on the density of the body tissues through which the X-ray photons are passing. So denser tissue, such as bone, increases the probability of X-ray photons being absorbed in photoelectric interactions. The result is that fewer X-ray photons pass through these areas of the body to reach the image receptor, and so those structures appear lighter. Body structures that readily absorb X-rays are called radiopaque. Those that less dense structures have a much lower probability of absorption, and they are said to be radiolucent. Also, if we're talking about equipment in the X-ray department, there are other things that we can say that are radiopaque and radiolucent. So the slide boards, the C-collars, things like that, those are radiolucent. The sandbags, the lead aprons, those are radiopaque. It is important for the radiographer to understand the atomic level interactions, but it is also important to relate these transfers of energy to a macro level where radiation dose and damage is more apparent. Macromolecules are large molecules made up of thousands of atoms. When an X-ray photon interacts with one of these atoms as previously described, the energy transfer may manifest as a change to the structure of the macromolecule. The three most common effects are main chain scission, cross-linking, and point lesions. In main chain scission refers to a breakage of the major structure, the framework of the macromolecule itself. In cross-linking, it is the result of the formation of limbs as a result of irradiation that stick to adjacent parts of the macromolecule or neighboring molecules, creating unnatural framework. The third one is point lesions, and these are the result of damage to a single chemical bond. So think of these as a wound to the macromolecule that may cause a malfunction of the macromolecule and damage to the cell overall. The most sensitive of molecules is the DNA. Among the contents of the human cell are two types of nucleic acids. You have the DNA, which is the deoxyribonucleic acid, and the RNA, which is the ribonucleic acid. The most sensitive of these molecules is the DNA. And you may recall that DNA has a coiled helix shape. Maybe you learned this in your anatomy class. But the coiled helix shape is created by its configuration of two sugar phosphate chains connected by pairs of nitrogenous bases, a twisted ladder. So it looks like a twisted ladder when you see it. DNA is the essential ingredient of our chromosomes. So the chromosomes are tiny rod-shaped structures segmented into genes. Damage similar to that described above may occur in DNA as a result of radiation exposure and could manifest as a range of responses from minor damage that is reversible to a malignant response and permanent damage. Genes contain the instructions for every cell, and that's the heredity. This is a critical reason for the radiographer to be mindful of radiation dose and make every effort to limit that dose to the patient and themselves. Finally, because the human body is about 80% water, irradiation of water, which is the interactions between X-ray photons and water molecules, can create harmful free radicals that then indirectly damage molecules and cells. So if you look at the figure 7-8 here, it shows damage to macromolecules. The three most common effects of X-ray photon damage to the macromolecules are the main chain scission, the cross-linking, and the point lesions.